You can see my screen?
Looks good.
Okay, great. So I can't ignore today's date. And so happy May the 4th to everyone. So I want to tell you about discoveries of extreme transients. This is by no means a complete sample or comprehensive or representative in any way. It's just a series of events that are extreme in some ways that are of interest to me, and I think are not fully explained by theory yet. Though there are ideas, some of them there are not even ideas. So I'll just take you through things that are extreme in different aspects. Please feel free to ask questions during if you want, because we'll be going through several different types of things.
Yeah, I'll try to watch. Raise your hand, and I'll try to watch for that while Iair's giving his talk. Okay,
you can also do it Israeli style, where you just interrupt me. But I don't know, Tony, if you'll allow that, but that's fine with me. Okay, so I want to show you one event which is too energetic for its own good. So normally, when I say normally, this is something that was not normal until 1987. 1987A is this the nearest supernova in modern times, of course, was we now know the explosion of a blue supergiant. Normally it explodes and you get a light curve that looks like this. So here's 1987A, and here's an event discovered by the Optical survey, which looks exactly the same, but is like an order of magnitude and a half brighter and has a much longer rise time. And just those two facts make it impossible to explain. And so let's talk a bit about the rise time in a supernova, because we'll need this later when we'll have events that are extreme on the other side of the scale. You have some, this is the most basic assumption, central energy deposition has to diffuse out through a ball of mass m, radius r. This is the time scale for diffusion. But in a supernova, of course, the radius is expanding with time, so the radius is a function of time. And so if you plug that in, you get that the diffusion time is a function of time. The diffusion time decreases with time. So time goes on, and the diffusion time scale is getting shorter, and at some point these two things meet. The diffusion time equals the elapsed time. And when that happens, this is at the time at which it happens. And so supposedly at that time, everything that was injected into, the energy that was injected can be released. And we see it as light. And so this is considered the rise time of a supernova. So it's very useful to remember that rise time tells you, the time elapsed basically tells you what mass you're looking through. And so you can assume some opacity and you measure the velocities from the spectra, and then you can get how much ejecta mass there is based on how long it took this thing to reach peak luminosity. So there's that expression on the left, and from the spectra you get the velocities, and you can plug that in and you get a mass. And so the mass you need to explain the rise time seen in this event is like 60 solar masses. If you multiply that by the velocity you see here squared, you get that you need an explosion energy of the order of 10 to the 52 ergs, which is an order of magnitude more than a typical supernova and more than what the neutrino mechanism can produce. And this was thought to be, if we know one thing about supernovae is that neutrinos cause them to explode, but not this one. And so there needs to be an additional power source here, which is not the regular one. And the authors of this paper look at a magnetar depositing energy in the center, a newly formed magnetar. Or this could be a current stability supernova, which I'll mention a bit later. But none of these models really fit the observation. So this is an open question. This one event that was brighter, too bright and too slow, slowly evolving, that we just can't, it just breaks the standard models, and we don't yet know what the additional power source here is. Okay, so that is something that was very slow. Let me show you things that are too fast for their own good. And so again, here's the typical situation, not a blue supergiant this time, but a strict star. So a star that lost its hydrogen envelope and sometimes helium envelope, explodes as what we call a type 1 DC supernova, stripped envelope supernova. You'll see here the rise time is typically 20 days. That matches nicely the amount of mass we think are in these explosions, so these work well. But we've recently or lately started discovering events that rise much faster. So you're seeing here one of the first samples from Maria Drought on the left. Things that rise in half that time or even less, just a few days. We found events that rise equally fast and are even more luminous, and that is even more of a problem. With K2, Armin Rest was able to find this beautiful something, we don't know what it was, that rose within a day to a peak magnitude of -19, like the type 1a supernova, and then declined. This is a problem because, as I said, the rise time can be equated with the amount of the mass ejected. You're seeing here on the bottom x-axis the rise time, and on the top axis how much mass that equals if you assume a certain opacity and standard velocity. So you see that 10 days rise, 20-day rise is about a solar mass of material, and 1-day rise is about percent of the solar mass of material. So that's the horizontal axis. The vertical axis is the peak luminosity, and this is determined by a standard thing that produces light in the supernova is nickel decaying to cobalt decaying to iron. So the amount of nickel you have will determine the peak luminosity. So there is an area here where you have high luminosity requiring a lot of nickel, but a short rise time, which requires small ejecta mass. And so you cannot have less ejecta mass than nickel, and nickel is part of the mass. And so this whole area is blocked off. It's not supposed to have any events in it. Right, you need more nickel mass than total mass, basically, which is unphysical. But then we go and find events in this restricted area. And this is very disturbing to have events there, which cannot be explained again by our standard, not that it doesn't require more energy, just the way the energy is released doesn't fit the standard supernova mechanism of a central nickel decay. So there are other ways to power events, interaction, magnetars, other things. And so could this be related to that? So some of these events we have spectra, most of them we don't. Again, because they're rapidly evolving, it's very hard to get follow-up data. This is one of the observational challenges. But for those that we do have spectra, so one surprisingly has a lot of hydrogen. You're seeing here in blue the spectrum of this one event, which is in the forbidden area, compared to standard type 2 supernova. It's not identical, but it has a lot of similarities, meaning that the last thing we expected was a hydrogen envelope for one of these things. Another event looks like a broadline type 1c supernova. These also known as hypernovae events, which have very high velocities, usually associated with gamma ray bursts, but most of them are not in this area of phase space. One, which is in this deep in the forbidden area, which just has a blue continuum with no obvious features. And then another one, which is a blue continuum on top, it's broadline 1c supernova on top of a blue continuum. So every event we get a spectrum of looks different. And none of them have can be easily explained by any of the alternative power mechanisms of supernovae. And so for most of these, we don't know how they are, how they emit light this way. But we probably know that, we know there's probably a diverse population here because it's not just one explanation. We need to find several explanations to explain the different types. One of the best studied ones was 2018 Tau, which is one of the best studies because it was one of the nearest ones, and so there's amazing data for it. Again, very luminous, very rapid rise, very rapid decline, featureless spectrum that then had broad features and then narrow features. I'll show you a close-up of this in a second. So there was suggestion that this could be tidal disruption event around an intermediate mass black hole, that this could be powered by a central engine like a magnetar. There are several papers on this. One of the papers pointed out that the light curve is not that dissimilar than a certain subtype, not well understood either, supernova called 1BN. 1BNs are, so the 1 stands for no hydrogen, the B stands for helium, and the N stands for narrow lines. So narrow helium lines. And indeed, the 2018 Cow showed narrow helium lines like 1BNs do. But that doesn't solve the problem because we don't know what 1BNs are either, even if this is one of them. And so normally 1BNs, there is no normally because there's only about 20 known and we don't even know what they are, but narrow lines of helium mean that there must be some slowly moving helium wind that the star is exploding into and no hydrogen. And so the idea was this might be a massive star that was caught as it was losing. It had already lost its hydrogen envelope and was caught caught as it was losing its helium envelope. You'll see most of the light curves for these events are rapidly evolving, which is not what you expect from interaction with circumstellar material. When the interaction is with hydrogen, we call them 2N supernovae, and the light curves are all over the place, and they're long-lived and luminous. But for some reason, when the interaction is with helium, most of them it's very uniform, except for these two long-lived ones. All of the rest that we know of are very similar and rapidly evolving, which is the opposite of when you have interaction with hydrogen. To make matters worse, there's this 1BN, which was found here, where the square is, and you're seeing here an HST image, which has a very, very strong limit on the star formation rate. This is a central cluster galaxy, the outskirts of the central cluster galaxy, where there is no discernible star formation rate, star formation going on, to the lowest rates of any core collapse supernova. So the title of this paper was actually maybe 1BNs we got them completely wrong, and they're not even massive stars, literally, or at least some of them aren't. And so, we're even stepping back to the question of, is this even the explosion, the collapse of a massive star that's producing these things? Speaking of things that happen in weird places, so another type of rapidly evolving transient, which is kind of more well established now, are these calcium strong events. Of course, a lot of work done at Carnegie on these as well. They are preferentially found very far from their host galaxies, again, indicating that these are not likely explosions of massive stars. Their photospheric phase is quite diverse, but they get their name from the fact that in the nebular phase, which happens quite quickly, within about a month or so, they have very strong calcium to oxygen ratios. And this is kind of what defines a class, this and the rapid evolution, but it is still not clear what the progenitor systems are, why they produce a lot of calcium, and why they not only happen in the outskirts of galaxies, but seem to prefer the outskirts of galaxies, which is very strange. Part of that could be an observational effect, but I think it's been shown that it cannot completely explain the observed locations. And so here's an example light curves of these events, also very quite uniform in terms of their light curves. Again, rapidly evolving, indicating that there is not a lot of mass. And since then, there have been more events that are even more rapidly evolving. So on the right, you're seeing a plot where the x-axis is the decline rate, how many magnitudes it declines after peak within 15 days. So in black, you're seeing type 1As. And then if you go way to the right, you're seeing several new types of events that are declining even faster. And so these generally, these events are known as rapidly evolving transients or fast blue optical transients, because as I showed you, many of them have blue continua, F-bots. So this is a paper also from people there at Carnegie. Again, taking a step back, like maybe these not only are not massive stars exploding, but maybe they aren't even stars exploding at all. But transients, TDs happening, tidal disruption events happening around stellar mass black holes. We'll talk more about tidal disruption events a bit later. But the idea is a star being disrupted by a black hole, and peak optical luminosities, the time scales, the X-ray luminosities for the events where we have X-ray observations, all seem to match these events. The rates are a bit lower than inferred, but again, we said this is a diverse class of events, so you don't have to explain, or you shouldn't have to explain all of them with one scenario. So this could definitely be a scenario that explains some of them. So this is very, very interesting. I think
accepted. I got a proposal accepted on one of the space telescopes.
Okay. As I said, this is very exciting. I think when you're observing something that is so not understood that you're just, we have models on the whole scale of what could cause these kinds of transients, which is really fun. And then, of course, thinking what kind of observations we need to get to distinguish between the models. Of course, the fastest thing we saw was the famous kilonova. Here on the left, it is compared to other things that I called fast until now. The fastest ones we knew by then, you see it's much, much faster. And on this scale of rise time and peak luminosity, it's on the corner there. Of course, that we know is not powered by nickel. We know it's powered by the creation of heavier elements. So it's okay that it's there. We don't expect it to be, we don't expect it to have to adhere to the nickel prohibited area. But when you take all of the data combined from this event, from the UV to the infrared, which is what you're seeing here, you cannot explain it with a single model of radioactive decay of heavy elements. Forget nickel, just take lanthanides, whatever fraction you want. You need to input here the ejecta mass, the ejecta velocity, and how much fractions in heavy elements. And you can explain some of the data some of the time. So you can explain the optical. If you want to explain the optical, then you under represent the UV, and you over or underrepresent the infrared at late times and the UV at early times. You cannot explain this with one set of parameters. So people have tried different things. One of the things people have tried is to explain it with 3 sets of these parameters. So 3 separate ejecta components where you set the ejecta mass, velocity, and lanthanide fraction separately. And then you can explain all of the data points all of the time. But is this even physical? So there is the idea that in neutron star merger, you do have 3 mass components, the tidal tails, from the tidal interactions of the neutron stars before they merge, the ejecta coming from the poles when the neutron stars come into contact, and then the winds from or a disk or winds or outflows from the merger product. And the nice thing, the very tempting thing is if you can really discern how much mass is in each of these components, that's extremely powerful because the tidal tails are influenced by the mass ratio of the neutron stars. The polar ejecta is influenced by the radii of the neutron star because this determines how deep in the potential well this ejecta is coming from, and then hence what its velocity will be and how irradiated it will be with neutrinos, which lowers the fraction of heavy elements and makes it bluer. And the merger product, of course, if it's a black hole or a neutron star, will affect the outflows from that. To the level of, people were saying there was a neutron star here that lived for a few milliseconds, and we can tell that because that is what would produce the type of ejecta needed to explain the light curve. And so it is very tempting to want to do this, and if it's true, it's very, very powerful. Obviously, together with the gravitational waves, you can get here then estimates of the individual masses of the neutron stars and the radii, which can constrain equations of state, together with the merger product. So this is extremely desirable. But there are other interpretations for how to explain the light curve. So the multi-component radioactive decay is the one I just told you about. There are people say this is still a single mass component with varying opacity in time. There are people saying this is boosted relativistic ejecta, which is causing the blue emission. And Tony and Juno over there at Carnegie had suggested that also some component could be coming from shock cooling of an envelope, like we see in supernovae, could also be responsible for some of the early blue emission here. So it's very important to be able to distinguish between these models if we want to make robust conclusions about physics going on in these events. And here you're seeing the early data again, twice. The data on both panels is the same, and I'm showing you 4 different models, 2 on the left, 2 on the right. The solid lines are various radioactive decay models, and the dashed lines are shock cooling or other things. And you see that the models differ at only at the very early times. And so we really, conveniently, they converge on the existing data. Of course, this is how they were built. But if we could get data at the very early times, and this was discovered 11 hours after merger, we need to be quicker than that, and we could distinguish between the models. Namely, shock cooling rises really fast, and radioactive decay takes a bit longer to rise. Rises more slowly, and so if the early data point is up here or down here, the earlier we get it, the more distinguishing it is. Even just one data point would be. If we had gotten it at this event, we would have.
It's always curious how the theorists agree when there's data and they don't agree when there's not data.
Yes, but yes, this is natural. I mean, the theorists built these models around the existing data, so they would not have been published if they didn't agree with the existing data. And they are allowed to do whatever they want where there is no data. So our job is to get data there and to check. And the frustrating thing about this event is we could have gotten data 5 hours earlier, but there was this delay in the localization because of a glitch. Because of a glitch and apparently because it took an hour to formulate the circular. But okay, that aside, we ask ourselves, moving forward, how do we discover these events even earlier than we did for this one? So this is very challenging. But there is even another reward for finding it very early. There's this prediction about the leading part of the ejecta, the fastest moving ejecta should be free neutrons, and they decay into protons and emit a blue flash of light as well, which is detectable with current surveys. But if you look at the x-axis here, it peaks 1 hour after merger. So super challenging, but even more motivation to try to find these things on these time scales. Okay, so how do we do that? I want to tell you about a project we're working on called the treasure map. And so the idea is that wouldn't it be nice if we could get all of the follow-up resources to coordinate their search for an electromagnetic counterpart? Next, there's a trigger. We don't want everyone overlapping, searching the highest probability region first, and missing the kilonova going on somewhere else. So in a perfect world, everyone would coordinate with each other. Now, obviously, it's a very competitive field. That is not a reasonable expectation. But what we can do is build a system where people who are interested can at least report where they are planning to observe and where they're observing in a robotic way. And people who are interested in that information can use that and decide, okay, what I'm going to do with that information. I'm going to search where everyone is searching, or am I going to search somewhere else? And kind of let it organically coordinate itself. So we're not obviously imposing anyone's search in a specific area, but we are building the tools to allow people to share where they are searching and use that information to decide where to conduct their own search for other people. And so this system exists, and it was operational during 03, and we're getting community input into how to use it, and we keep adding features. Some of the searches involve looking at specific galaxies, and so you can now also report to the treasure map your galaxy ranking, or you can get other people's galaxy ranking. If you just have a telescope and want to know where to observe, it'll tell you, here are the top galaxies that this group thought are important, and you can see if no one's observing them, and you go for it. So hopefully in the next observing run, we can get a lot of community involvement in this, and this can make our searches much more effective, and we can find the kilonova very early and do all this cool science.
I mean, I guess, how does that work in practice? Because let's say, are you expecting people to post their search plans before they actually do the searches? Because, it's kind of hectic. People are really, they have that hectic night. And so they might not want to post where they searched until the night after, the day after they searched. And then maybe it's too late for that planning.
There are a few types of things you can post, is where you plan to search and where you have searched. And the treasure map can show all of that information. And the idea is you can do this with the web form, which is not the easiest way, but there's an API. And so the idea is, for example, our search with the Supernovas Observatory is completely robotic. And so our algorithm, when it decides where to point, there's just like 3 lines of code that will report this to the treasure map. And then it takes no resources from us. And then every time it observes something, it updates the treasure map. Okay, I observed this, I did not observe that. And so all that information is already there. And then we currently do not have in our algorithm something that reads the treasure map and decides where to point based on that, but that is the next step. And once, even if your observatory is not robotic, if you have an algorithm that is trying to decide for you where to observe, this is like 3 lines of code that you can incorporate to report to the treasure map and query the treasure map to help inform your algorithm's decision. And so that is the idea. We're trying to make it as easy to use and as convenient as possible, because I think that is the key for getting people to use it.
And there's also depth of the observation information as well, because it's it's a 3-dimensional problem.
Yeah, absolutely. So there is both distance information in the localization and in the galaxies being chosen, and depth of any observation that you plan to take. You can even say, I plan to take this, but my depth is magnitude 17 or my depth is magnitude 22. That will influence if people want to observe it as well. And of course, once you observe something, you also report to what depth you observe. And this, any wavelength, optical, infrared, we're supporting now X-ray and radio searches as well. Gamma ray localizations are also supported if there's a GRB. And we're looking to add neutrinos as well. If that happens, they can report their localization as well. And so we're trying to support all wavelengths here. Okay, so I want to show you my favorite supernova. So moving on from things that evolve too rapidly. to things that just don't make sense at all. And again, this is the most normally of all normalies. The most common supernova realized in nature is when a red supergiant explodes as a type 2p supernova. And it's called 2p because it has this 100-day plateau in the light curve, which is caused by recombination of hydrogen in the former envelope of the star as it explodes. And these events have a lot of hydrogen from the envelope, and that is the main feature in the spectrum. And so 1999 EM, the prototypical of these prototypical explosions. And here's one called PTF14HLS shown next to it, which is a slightly lower signal to noise because it was more distant, but basically the same thing spectroscopically. So if you just see the spectrum, I would have bet my car this is a type 2p supernova. Luckily, I didn't. Because the light curve was completely different. And so normal 2p, 100-day plateau, and then a drop. This thing went on for 600 days, actually went further on for 1,000 days, with at least 5 different peaks in the light curve. Very, very unusual, and more luminous than a typical type 2p. What's even more unusual is in a typical supernova, the spectrum changes with time. You're seeing further and further in. And so the lines get narrower. You're seeing the slower material later in a very predictable way, or a very at least calibratable way, in that you can even tell the age of the supernova from how broad the lines are, except for this event where the lines did not get narrower with time. At 600 days, you would have thought it's a 60-day-old supernova based on the width of the lines. So they did get narrower, but very, very, very slowly. And this really is really hard to explain because you can say, okay, the velocity is constant, that maybe that just means everything is moving in bulk. You don't have a velocity gradient, except you do see a velocity gradient because you see iron moving slower than hydrogen. And this is typical of a supernova. You're at any given moment, you're getting a picture of where the hydrogen out here and the iron further in. And so you're always seeing iron slower than hydrogen. So this is telling us there is a velocity gradient, but the photosphere is not receding into this material, because in normal supernova, if you wait a while, you'll see hydrogen now where you saw iron before, and that doesn't happen for this event, and I don't know how to explain this. Another bizarre thing is there was an image taken of the supernova here on the left in 1954. It was seen exploding, and then there was nothing in 1993, and then of course nothing until 2014 when it exploded again. And so that is also not typical of a star to explode twice, or we don't even know how many times in between.
Where's the historical data from for this?
This is the POS, the Palomar Observatory Sky Survey. So there was POS 1 and POS 2. That's all we have at these epochs. And one you see a source, and in one you don't. And so we don't know what happened in between, but even that one that got caught in 1954, 60 years before when we thought it exploded, is very strange. So the combination of this weird light curve, weirdly evolving spectra, 1954 eruption, the radii you get, there's no single model that explains it. It's definitely, that is no type 2p supernova, that is something else. And so there are several models that try to explain it with different physical mechanisms. Common envelope supernova, this is where a star spirals into the envelope of another star and explodes. Circumstellar interaction, magnetar power, fallback accretion, pulsational paired stability supernova. And again, each of these models explains some of the properties of the supernova. No single model explains all of them. And so I think the jury is still out on what this is, even though we've tried. And there's now been another one, which was caught earlier than this one. So hopefully that data might be informative. Okay, I want to move on in the time I have left to tell you about things we're finding in galaxy centers, which we think are not exploding stars, but again, we're not entirely sure what's powering them. And so Tony mentioned this discovery we made in 2014, which has since the sample has increased of this class of events, quite luminous, quite slowly evolving, very blue. You're seeing the spectra on the right after continuum subtraction. They're all riding on the blue continuum with weird features. Some of them have hydrogen, some don't. All of them have helium-2, broad helium-2. The structure of the lines is very strange as well. And they all happen in galaxy centers. And so the idea is these are tidal disruption events. where a star gets close to a supermassive black hole in the center of the galaxy and is disrupted. You're seeing the analytical picture on the left from Martin Rees, where half the star is ejected and half is bound to the supermassive black hole. The numerical simulation on the right shows this is a bit more complex, and even this is without all of the physics in the simulation. And so it is a very complicated problem, and it is very difficult to model. And it's also very difficult to understand why the events look like this. And so the expectation was initially that this half of the star that is bound will somehow return to the black hole, circularize, accrete, and the accretion disk will emit X-rays. And so indeed, people looked for TDs in the X-rays and found them in the X-rays. But no one, it took a while to find them in the optical because this was not where they were expected to emit. And indeed, when we had the first set of events, they were in the center of galaxies. The decline rate was kind of, you could fit this canonical mass return rate in a TD, but the temperatures were 1 to 2 orders of magnitude too low, right? They were emitting in UV optical rather than in X-rays. The radii you get from the black bodies are 2 orders of magnitude too large. The total energy, even if you ignore the details, just the total energy is too low. You expect the accretion disk to have evolving temperature. These have constant temperatures, and why a third of them show no, including the first one that was found by Suvi Gazari, show no hydrogen was a mystery. And so initially we thought, okay, these are not the TDs we're looking for. But as we found more and more of these events, we were convinced that, okay, they have to be that, because we have to find a way to explain these emission properties as TDs. And then theorists came up with 2 explanations. One of them is that there's some material, so there is an accretion disk, it is emitting in the X-rays, but it is being reprocessed by some material around this event, which could come from the star itself, could have been there before. This reprocessing material downscatters the X-ray photons to UV and optical, increases the black body radius, so the photosphere is formed further out, and this explains what we see. Alternatively, the accretion disk has not even formed yet, because it is actually not that easy to have the material lose energy and circularize. But what does happen because of GR precession is that the leading edge of the disrupted star collides with the trailing edge. And you get these shocks known as outer shocks. And these shocks do 2 things. They dissipate energy, allowing the material to circularize. But as they do that, they emit light at the observed radii, temperatures, and luminosities that we see. So the question is, are we seeing these outer shocks before the material even circularized, or are we seeing the accretion disk that's already formed being reprocessed by material? And of course, our goal is to use these TDEs to derive the properties of the black hole and understand the accretion physics. And we can't do that if we don't know what we're seeing. And so we thought we solved it with this event, but we didn't. This event showed declining optical emission with increasing X-ray emission right after it. And we thought, okay, this tells us that the optical emission was indeed coming from these outer shocks. Then they helped the material circularize, and then it generated the X-rays. But you can also explain this by, this was X-rays all along, just early in the event, they were being reprocessed by optically thick material. As time goes on, this material thinned, and now you're just revealing the X-rays that were responsible for this all along. And so that did not solve the problem. But since then, we found events which have like what looks like multiple components in the light curve. So you're seeing here 2 peaks in the optical light curve, and you're seeing the X-rays, the triangles here that grow at later times. And so again, the question is, could this be evidence that there are 2 mechanisms at work, these outer shocks and reprocessed accretion? Here's another event where you see clear 2 components. And a nice thing is spectroscopically for one of these events, when you see the X-ray rise, you see the iron lines go down. Iron lines are thought to be caused by reprocessed X-rays. So that is actually telling you, no, the X-rays were there all along. Early on, they were making these iron lines, and once the material thinned, the X-rays are free to escape, and you see the X-rays and you no longer see the iron lines. So it could be that we have both mechanisms at work. It could be that it's always emission from the X-rays being reprocessed at different levels as time goes on. Another thing, my favorite puzzle about these events, which again Tony mentioned also in the introduction, is where they happen. They happen in the centers of galaxies that are in this weird part of space. And so you're seeing here all SDSS galaxies in gray and galaxies with TDs in red, and one of them here also in blue, which are concentrated at the corner of these plots, except for one, but there's a good reason for that one. All of the other ones are in the corner of this plot. This plot is showing H delta absorption on the x-axis and H alpha emission on the y-axis. So H alpha emission, the higher it is, the more star formation you have going on now. So things at the bottom have no star formation going on now. H delta, the stronger it is, you have an absorption, it tells you there was a lot of star formation in the past. So these galaxies concentrated in this corner have no star formation now, but had a lot of star formation in the past. So these are post-starburst galaxies, which are very rare, but seem to host most TDEs for reasons that we don't yet know. It could be related to the fact that these galaxies have stronger central, strongly peaked central densities, which might affect the TDE rates. But there's no definitive answer to this yet. And so the more events we find, the more statistics we can do. But this is still a puzzle.
So yeah, you're careful there about saying optical TDEs. So for more X-ray bright TDEs, do we know where they are in this diagram? Are they in the same spot?
Right. So for many of them, we don't have a characterization of their host galaxies. The most famous X-ray, or even like beyond high energy TD, is Swift J1644, which was not seen in the optical, was seen in gamma rays. So that was too high energy than expected. And that one is thought due to a jet pointing in our direction. The TD is also in those types of galaxies. But for many of the other non-optical events, it's a more diverse class in terms of the transients themselves. So it's hard to know if they're all the same. And then they're also more diverse. For the ones we know, the host galaxies are also more diverse than the host galaxies. Once you take a kind of clean sample of all the optical events showing these broad helium lines and these types of line curves, then you see the strongest post-starburst association. But the more heterogeneous you are allowing of what you call a TDE, then the more heterogeneous the host galaxies become as well. Okay, so but we obviously looking for more TDEs, we start finding things that we don't know if they're TDEs that look even stranger. This is an example of one found by the Assassin survey. This is Assassin data you're seeing here. So it is quiescent, and then flares and then stays there. Okay, so it doesn't go down like a TDE that goes up and down. You're seeing here the light curve, both X-rays and optical and UV, they all went up and just stayed there for years. They are declining very slowly, but in gray here, you're seeing a typical TD, and this is not that. This is declining much slower. So there's some flare, but then it stays at this heightened state. Spectroscopically, they're also different. They have similar line species, but much narrower. So the ones at the top are the ones until now I showed you, these broad line TDs. The ones below them are also showing helium-2, but much narrower. And thanks to the fact that it's narrower, you can also discern other lines. And you see the series of lines known as Bowen fluorescence lines, which require a kind of hard continuum to excite some cascade of lines, which you see in these events. These are actually predicted to happen around AGN in the 80s, but this is the first time where we actually observed this. And as far as we can tell, these events, whenever there's archival data of the host, they used to be AGN. They happened in galaxies that were active before. So this might involve the pre-existing accretion disk of the AGN, either some instability or TDE happening through that accretion disk, which is also something that can and should happen. But for that, we have a better candidate, I think, which is this one, related to another unexplained phenomenon in galaxy centers, or not well understood, changing look AGN. Here, you're seeing a spectral series with time going up. So the bottommost spectrum is an archival spectrum of this galaxy, 2001 narrow line AGN. And then in 2018, it flared and became a blue continuum. And then as time goes on, broad lines emerge. So when you at the top, it's now a broad line AGN. And this is known to happen. AGN have been caught in both states. The same AGN, one seen this way, the other seen that way, and in both directions. But it was never caught as it happened. And so this thing, again, discovered by Assassin, you're seeing this non-detections and then a flare that went up and down. And if you just look at the light curve, it's kind of similar to a TD light curve. It does go down in this t to the minus 5/3 rate. But of course, the spectra are completely different. It's a type 1 AGN turning into, narrowline AGN turning into a broadline AGN, like going through a blue continuum in between, and you can actually measure the time it takes the broadlines to appear. And while all of this is going on, the X-rays turn off and turn back on. So the middle panel here on the right, you're seeing the X-rays. They're archival level. They went below that and then restored. And what you're seeing, the nicer data here is it's not noisy. It's actual variability on very short time scales. NICER was able to get a spectacular time series of just very short time scale variability while this thing was turning off and on again in the X-ray. So we have at least 3 papers on this, and none of them are clear on what is going on. There are some ideas. But maybe if TB were to happen in an AGN, maybe it would look like this, and maybe it would trigger the change in look, but this is very speculative. We only have one example of this. Okay, so let me summarize. What I told you here is I showed you an example of an over-energetic supernova that defies the standard explosion mechanism, and we don't quite yet know how. I showed you rapidly rising luminous transient that cannot be powered by centrally deposited nickel. But also we don't know what they are powered from because the spectra all look different. I showed you explosions that happen far from star forming regions like 1BNs and these calcium strong events. Same for calcium strong events, we kind of come to terms with the fact that they're not massive stars exploding, but for 1BNs, this was kind of surprising, if that's really the correct interpretation. I've shown you very peculiar events that telling us something completely different is happening there. Now that we've started focusing on galaxy centers, we are finding new types of transients related to supermassive black hole accretion that we don't yet know what is going on. And even when we think we know what is going on, we don't know how that is being translated to the emission that we see. And so we are finding more and more events, and we need help from theorists. You're our only hope to understand what is going on here. And this is especially acute given that more and more, we're going to find more and more of these and more strange things. With these surveys coming online, of course, LSST, but also our follow-up facilities that are allowing us to do rapid follow-up for these rapidly evolving events. These are just some projects I'm involved in. So SOX, Son of X Shooter, is going to be a spectrograph dedicated to, for most of its time, to transient, real-time transient classifications. Sitting on the same mountain as BlackGem, a new rapid transient survey in the Southern Hemisphere with high cadence. You're seeing here 3 telescopes that will be scanning the sky at high cadence for rapid transients. And I'm also very excited to tell you about an Israeli-led project, UltraSat, which is going to be a space UV survey, so wide field UV survey, which can find sharp breakout of supernovae, tidal disruption events that are bright in the UV, early blue emission from kilonovae, of course, things, flaring stars, things that we don't even know flash in the UV because we've never searched that area in the sky with a wide field survey before, but this is coming, and so we're very excited about that. And so, yeah, I think even more perplexing. Hopefully, these this data can help us explain things we don't understand yet, but I'm sure that will also present new mysteries and new puzzles for us to solve. So, thank you very much. I hope those weren't too many Star Wars puns, but I had to because of the date.
Great. Thank you for that whirlwind tour through all different types of unique transients. Are there any questions? You can raise your hand or just speak up if you have a question. I guess I'll just start off unless we have other ones. You showed all these different types of transients. There's different mysteries. Do you think, what's the way forward for progress? Is it just sort of brute force of just finding as many of these as you can, and they're rare, so you just keep looking? Or are there more creative strategies observers could take to try to solve these mysteries?
Yeah, I think it's a combination of things. I think it's finding more events so you can better map the population. getting better follow-up data of these events, because now it's become relative. And once you have transient surveys scanning the whole sky, they're there. But knowing that they're there and getting the required follow-up data in time is still a challenge that we're dealing with. And so getting the multi-wavelength follow-up quickly, I think, even of the same number of events, would be very helpful, especially if we can do it for more events. And yeah, I think this requires a lot of coordination and between wavelengths and between facilities, because these things really disappear quickly. So I think, yeah, combination of more and better observed at wavelengths that maybe we haven't until now. And of course, more models and more things to test and more things that will tell us where we should focus our observational efforts on is, if you would have told me early UV emission for the kilonova before 1717, I would have said that doesn't, I wouldn't invest, or maybe we shouldn't invest in early UV observations following gravitational wave alert. But turns out that is super important. And so, or maybe you knew that, but I didn't know that.
Well, the first models that we had with Brian Metzger that were wrong, they were bright and blue at early times. And then the theorists tried to get smarter and do better opacities. And then they got redder, which ended up being less like the observations, at least early on.
Right. So, but those kind of things that can really direct where we should focus our efforts and resources to get the most distinguishing data is going to help a lot.
Alex, go ahead.
Hey, my question is about, you talked a lot about sort of classes of transients for which we don't have an idea of sort of what the progenitors are. But I guess what I'm wondering is, in terms of the ones where we do understand what the progenitors are, is there room for sort of improving what we can learn from those things with these sort of follow-up? That's sort of like Absolutely. Relating back to sort of the populations of the massive stars and that sort, or whatever the populations are.
Yes, absolutely. So even for what is now considered established like core collapse supernovae, I think one very exciting frontier, which I enjoy a lot, is very early data of core collapse supernovae, which Tony's done a lot of work on the shock cooling emission from these events, which is just once you get the early data, you can actually map not just kind of the radius of the progenitor before it exploded, but its density profile, which is an excellent constraint on stellar evolution models. And so to me, this is very exciting, and very early spectroscopy, for example, of established classes of core collapse supernovae has suddenly revealed that they do have some confined circumstellar material, telling us that they do have a very violent episode of mass loss right before they explode, in kind of the years before they explode, which is also a very interesting constraint for stellar evolution models. And so this is, to me, an exciting new frontier to better understand the final stages of massive star evolution and how this connects to their explosions. And there's still many open questions there. And the nice thing is the same techniques that we're using to find rapidly evolving transients, even if the transient ends up being a kind of established type 2 supernova, the early data is still super exciting and super useful to gain new insights.
That's great. Thank you very much.
Yeah, and I think ultrasat's going to be especially good in that respect. Can you remind us how it's wide? It's pretty wide field, or what's the
it's supposed to. Okay, so we're negotiating this now between the teams involved in ultrasat, but it's a 200-something square degree field of view, and the original plan was just to stare at a single field for as long as it can continuously, and then move to another field per season. But then they got people like me interested in TDEs involved, and I said, actually, I'd rather you kind of scan a larger part of the sky, less continuously. So this is being debated, but it looks like at least 90% of the time you'll be staring at one field, which the idea is to just find very quick flashes of UV associated with shock breakout and things like that, which is super important tonight. And even though I'm the TDE advocate for this mission, I do not oppose that they do that. And so this is looking like the main strategy is going to be that.
All right. Well, thank you. If there's not more questions, I just want to remind you, Iair was nice enough. It's pretty late there in Israel now, but he's agreed to meet with people for one-on-one meetings tomorrow, and we've been distributing the schedule, and there's still a few slots left if you'd like to talk with them. But otherwise, thank you for the really nice talk, and have a good night.
Yeah, thanks. Have a good day there, and
thank you.
Again, happy May the 4th, and we'll see some of you tomorrow.
Thank you very much.
Bye.
Great, thank you.